Welcome to the pre-recording of lecture 32 of Introduction to Supercomputing. So in the lecture of today, we're going to address memory coalescing techniques, how to avoid bank conflicts, and how to develop data staging algorithms. So this is a lecture on GPU acceleration. GPUs are graphics processing units, chips capable of performing 1 trillion floating point operations per second. For that to happen, we need data parallel algorithms, and our algorithms need to be outlined at a sufficiently fine, detailed levels, so at the instruction level. Also, one needs to have sufficiently many tasks or threads that need to be defined in order for teraflop performance to happen. So we talk about acceleration. So blocks of threads are launched by the central processing unit called the host, and the device accelerates the computations. So one benefit of using GPUs is not only the capability for doing trillions of floating point operations, but also for the increased memory bandwidth, also expressed in tera orders, so terabytes per second. So, but for that to happen, we have to be very careful how threads access memory. And what we actually want is that all threads coalesce in accessing memory. And we avoid bank conflicts. Data staging algorithms will make sure that adjacent data locations in memory are accessed by adjacent threads. So this is essentially the essence of the lecture. Okay, so we have memories. So there is the random access memory on the host, and then there is the global memory on the device. So there is the memory transfer from the host to the device we need to be aware of. But on the device, the data is moved from global memory into shared memory and from shared memory into registers. So doing so seems to complicate things a lot, but it adds additional instructions and helps in the latency hiding, as we discussed in the last lecture. So when you want to access an element in data, a data element, so typically you cannot address a single byte, or perhaps you can, but typically you do multiple bytes when you access a 64-bit float. And essentially, you can also at the same time access memory, many locations that are consecutive to the current position. So it is therefore very advisable to have somehow data be put into consecutive memory locations if they are to be processed by consecutive threads. In order for reaching the advertised or the theoretical peak memory bandwidth. So the first definition is memory coalescing. So all threads are typically executed in one unit of 32 threads. And when one thread in warp accesses memory, then essentially all the other threads are having to do the same thing in that warp. So we work with threads that are bundled in 32, in multiples of 32. And the parallelism that you get is that the same time that it takes 32 threads, 32 sequential instructions would now happen in one instruction at the same time as one instruction. So what you actually want is that all the memory accesses are coalesced, happen essentially at the same time. And this happens if when the first thread accesses one memory location, then the next thread accesses the next memory location, and so forth. So you have 32 threads, you have 32 adjacent memory locations that are accessed by each individual thread in the warp. So we are considering this already, or actually only in lecture 32. So although this is actually when you consider GPU acceleration, it has a very high priority to actually consider the memory accesses. And it's not self-evident. So we will see examples where one may work on a first design which turns logical and correct, but which is not well performing. Here is how memory accessed is global memory accessed by a warp. So we have, so this is a historical picture, so still talking about compute capability 1 and 2. But it still matters, it's still very much relevant for today. So we see 32 threads that are going to access consecutive memory addresses. And there is also the bytes that are accessed at each location. Okay. Here is where it can go wrong. So there is the alignment and there is the misalignment. So we have threads that can actually switch. So here you have the compute capability 2 and higher, which allowed for a more irregular memory access. So, but then you have the misaligned memory addressing, where you have this threads that actually are accessing non-consecutive memory locations. Okay, so this comes from the CUDA programming guide. Here is something that the CUDA software development kit provides for you. So there is the double 2 type. The double 2 type makes that a sequence of 2 doubles are aligned for efficient memory access. And this is very convenient if you want to store a complex complex double then, that where the real part is one double and the imaginary part is another double. If we would define these doubles, these complex numbers with structs, we would have a misalignment. So that also, you could also see the alignment as a very compact representation of the data. So we have the alignment that is now in multiples of 128 bits. So one double occupies 64 bits or 8 bytes. So you do not have extra data that needs to be stored, as would be the case when you would use a struct in C to represent and to store a complex number. So this is where the software development kit helps you. It also is very useful if you want to work with multiple doubles, with double doubles. And the CUDA software development kit has also a double 4 type. Okay, so here is one kernel that one can use to examine what happens when misalignments occur. So what is the effect from misalignments on the efficiency and on the bandwidth? When you time these things, you have to make sure that you particularly time the kernel event and not the total wall clock time. But the point here is that if the offset is 1, then adjacent threads, so the thread identification number is here computed from the thread index within a block, from the size of each block, the block dim, and then the index of each block. And this is a simple kernel which copies. And this is the simplest example where you could observe the effects of misaligned memory accesses. Then there is the notion of bank conflicts. We talked about the accessing from global memory, but then there is also accessing from shared memory, or storing into shared memory, or reading from shared memory into registers. So the shared memory is organized in 32 banks. So 32, again, is a number that corresponds with the size of each warp. If you have, so you can see that using shared memory is very advantageous as far as the latencies go. So you have to wait much less. 100 times is mentioned here. I will mention the sources at the end of the lecture. 100 times faster accessing data from shared memory than from global memory. So what happens is that you have successive 32-bit words, so 4 bytes, into successive banks of memory. You have a bank conflict when 2 or more threads are going to access different 4 bytes belonging to the same bank. Okay, so what you want is that there is no bank conflicts. So there is the memory coalescing, which is high priority. Avoiding bank conflicts is medium priority. So here you see how your stride. So with the global memory, we were working with an offset with memory coalescing. With bank conflicts, we work with a stride. And in previous lecture, we discussed kernels, 2 different kernels for the reduction algorithms. I will return to this, but what you actually want is the example from the left here, where every thread, so the ith thread, works in the ith location, in the ith 4-byte position in the memory bank, in shared memory. You have in the middle picture, so it could go extremely wrong, where every thread is accessing the same location in a memory bank. So the difficulties that are certain to occur are with the middle and the rightmost picture. So actually the most dramatic case here is at the rightmost, where every thread wants to have access to the same number, the same 32-bit or 32-bit float number in a memory bank. So that's collision. So there is the irregularity, which is bad, which makes it cumbersome, most likely to compute the indexing. But then you also have the collisions that are happening. Certainly, it is very bad if every thread wants to store something at the same memory location. Okay, so I mentioned the reduction algorithm. So we discussed this kernel earlier. So this is the second kernel that avoids a lot of thread divergence. So here it's actually for 32, but imagine that we are working now with a warp size of 2, then there will only be thread divergence in the last 2 steps. So there is the if-else. Only half of the threads each time are collaborating, so the stride is halved in each step. So here what we do is we actually are having sequential addressing. So the ith thread is going to update the ith location in the shared memory. So we did not mention that explicitly, the benefit of rearranging the threads in this fashion, but it is not worth noting. So that's something that we discussed very early on. Also, you could kind of have it always arranged that the ith thread writes to the ith memory location. Okay, let's go to the parallel pattern of matrix-matrix multiplication. So a matrix-matrix multiplication is again very compute intensive. So now we get again to the nth cube algorithm. So n to the power 3, where n is the dimension. The reduction algorithms are memory bound typically. The matrix multiplication is a compute bound. So also there actually it matters a lot how the elements in a matrix are accessed. Either row by row, and this, if you make a product, this could be very beneficial to access the elements by row for the first matrix. The second matrix is accessed column after column. So depending on where the matrix is positioned in the product, first operand or second operand matters a lot. Okay, so when we first worked with GPUs, we were addressing the linear addressing system, so explaining how matrix, which is a two-dimensional structure, is actually mapped into one long array. So you can map the array row-wise or column-wise. And essentially this is what it means when you talk about a row-wise traversal or a column-wise organization of the elements in this two-dimensional table of numbers. So what is it here? Well, you see that here we have a row-wise organization. That would be the default order if you work in C with the double indexing, so the double bracketing, where the Aij, where you have the ith row and then the jth column, then you are by default working with a mapping of the numbers in this way. So you can see that the element 1, 3 is stored at the position 7, so the 8th position counting from 0. So you can can compute the 1 and the 3 from doing division by 4, integer division by 4 of 7. So 7 divided by 4 is 1, and the remainder is 3. So that gives you the 1, 3 index in the logical organization of the array. So why is that now important for memory accessing? So suppose that you would access in column by column. So then what happens is that in the first load, you load the elements at position 0, 4, 8, and 12. So you have 4 threads that have to access elements that are right quite far away from each other. Now here I can only draw 16 numbers on the slide, but imagine that this is a 32 by 32 matrix, so these are 1000 floating point numbers, and you have a stride that is actually 32. So if the shared memory is organized in banks, so adjacent threads are going to work into different banks. It also works, the same argument kind of also works for accessing into global memory. So it also works for memory coalescing. So if you have stored your array in a row-wise fashion, then accessing it column after column is going to be leading to a lot of bank conflicts. On the other hand, if you access your row stored matrix in a row-wise fashion, then you see that working now with warps of 4 threads, you see that adjacent threads will load adjacent memory locations. So this is for the default row-wise organization. You also have the column. You can make the same arguments for the column-wise mapping. So here this summarizes this. So in the default row-wise organization of data in a 2x2 matrix, the uncoalesced access leads to a lot of bank conflicts. It also will make the loading into shared memory slow, or not as fast as it should be. On the other hand, if you do the row-wise traversal, then actually you will have an instantaneous, so there is one instruction that's executed by as many threads in the warp. Okay, typically the good and the matrix multiplication that we have seen from the software development kit in the CUDA and also in the CUDA BLAS is working with tiled versions. So we are organizing the matrices into tiles where the tiles are loaded into shared memory. So the tiled matrix multiplication, we have discussed this in 3 previous lectures when we introduced GPU acceleration. Here we are going to rehash this, but now with the explicit computation of the rows and the columns indices. So we have the 2-dimensional thread organization. So we have blocks of threads where the blocks are organized in a 2-dimensional grid. So every thread index has a X and a Y index. So every thread index is double. So we have and then also we have a block index, which is also double. So actually we have a 4-dimensional structure. So this corresponds to the indices of the tiles in the first matrix and the tiles in the second matrix. And they are going to determine the axis, how A is accessed and how B is accessed. So the point being that that we do have coalesced memory access both for A and both for B. So here is the kernel again. So we do the loading from global memory. So these are 32-bit floating point numbers in the matrices A and B. We have the tiles that are declared here by this underscore shared. The tiles of width W, both for A and both for B. We compute the indices that are being used to load the data in the shared memories. The tiles for A and B. And then you see the accessing in the loop. So there's one register, so one float, the CV, which is going to store in a register the results from the one element that is multiplying one row from A with one column from B, stored in the tiles. So we have the synchronization that also needs to happen. Every thread needs to be done with its loading of its one element. So if we have tile sizes of 8 by 8, so 64 threads in one block are ready. So every thread is indexed by this TX and the TY into one block of threads. So one block of threads is occupied with one tile that gets computed in the result. Okay, so this clarifies the kernels that we have covered with matrix-matrix multiplication. So what does a data staging algorithm? A data staging algorithm will arrange the data, and the data is both input and output, so that we do have efficient memory coalescing. Again, the CUDA C programming guide gives the highest priority to having actually having memory coalescing. So that's necessary in order to benefit from the high peak bandwidth of the GPU. What it essentially always means is that adjacent threads are going to access adjacent data elements. So you will have as you load into shared memory, you actually avoid bank conflicts, but also the writing and the reading from global memory will go more efficiently as adjacent data elements in global memory are accessed more efficiently when they are adjacent. Okay, so let me now give two examples. So I mentioned the complex numbers. Complex numbers are composite data elements, although for complex numbers, for complex doubles, CUDA provides support with its double 2 data type. Now the parts, the real and the imaginary part, can be again multiple doubles. So I speak from experience. When we were working with quad double, with real quad doubles, we were still able to exploit the double 4 data type in the software development kit, but then we got into trouble with complex quad double. So a quad double consists of 4 doubles, starting with the most significant double, and then going to the least significant doubles. So if you are, so double 2, double 4, very convenient, but if you are scaling up to more accurate, you want more accurate results, so you're going to work with a higher precision. So you were going to have bank conflicts, and one can then no longer achieve very good bandwidth, and even in compute bound problems you will notice the performance dip. So what should you do instead? Well, the answer is you just, and actually it is quite a complicated result. It's a simple answer. Instead of working with an array of complex doubles, you use 2 arrays, one array for the real doubles and another array for the imaginary doubles. So instead of working with arrays of arrays, you actually work with one array, multiple arrays, as many as you need. If you work with complex quad doubles, you work with 8 arrays. This makes the code sometimes more complicated, but on the other hand, double arithmetic, quad double arithmetic is most often used in a staggered way. So you start with a double approximation that you then refine to double and then to quad double. On the other hand, often you want to drop certain data elements. So if you code in the way with working with multiple arrays, it's also very easy to drop data. If you work with complex numbers and you notice that the imaginary part are insignificant, then you can also drop those and easily transition in this way from complex to real data. Okay, so here is another example. So what you actually need to do here, so and this is a little bit of contrived application, but this example is to indicate that the problem description can actually lead to computation that is very bad for memory accesses. So we want to compute consecutive powers of consecutive numbers, and in the output we have that the first number is raised to consecutive powers, then the second number, then the last number, etc. So you see what the natural order will be. You will be that the first thread will actually read the first element, the second thread will read the second element, and the second thread will start to write the powers very far away from where the first thread writes. So if you follow the outline of the problem description and implement it straightforwardly, just using the formulas essentially of the input-output specification, then you will lead to a program that is actually not going to perform very well because of its bank conflicts. Okay, so here is one way to work. So you could, instead that you have, you could also work essentially with multiple kernels, that you have very multiple short kernels, but that would be very bad in the sense that there will be a lot of reading and a lot of writing from global memory. So you don't want this. So you want this in one kernel. So instead, each time when a power is computed, all threads are actually writing to shared memory. So, so this is actually the bad thing. I'm sorry if I introduced this wrong. So this is the naive implementation worked out with a stride. So what is pretty bad here is that instead of having the simultaneous computation, you will actually have serialized the computation because of the writing to shared memory. So you should actually rewrite the problem in a way. The problem was misleading the output. So what you actually should be doing is that you can. So we actually are talking about shared memory and avoiding bank conflict. So this is not yet writing into global memory. Also, you have to do the memory transition from the memory on the device to the memory of the host. So if the input output you cannot write to screen when you are working on the GPU, you could actually postpone the reshuffling of the data, let it done by the CPU on the host. Okay, but for the device perspective now is that you have that adjacent threads will now write their powers to adjacent memory location. So if you write the problem, the output of the problem like this, then it is very natural that you do not have bank conflicts. And now every writing will actually be close to the optimal speed up. So you will have already the speed up because the device accesses its memory much faster than the host, but you will have the additional speed up of the multiple cores that are available. Okay, I will end in the last 5 minutes with a very brief prototype version. So in a way, this is prototyping in Julia. Well, prototyping where you can also already experience the effects of bank conflicts and efficient memory access. It's mainly important that one gets familiar with GPU coding. What Julia does for you is that instead of having separate instructions for allocation, memory transfer, everything happens a lot faster. One needs to be aware, and that tripped me up when I wrote this here, is that the indexes in the array start at 1, and also the thread index starts at 1. So here, what is in this basic version defined is the computation of the powers, but now with in the very straightforward manner. So what you will have is that each thread writes to its own bank, essentially. So if we have 32 powers to compute, the ith thread will take the ith input element from A, and it will write into 32 consecutive memory locations in B. So this is the bad version. So I will emphasize this. The purpose of giving this version is that as an exercise is that you improve it. So I am focusing here on CUDA. There are other packages available for other types of GPUs. So that's another benefit of using Julia, that one can address, one can work with multiple different types of GPUs. There is the problem of overflow. If you would take consecutive integer numbers, then 2 to the power 32 is already a very large number. Here I took equally spaced numbers between 0.9 and 1.1. So this gives for very nice numbers in 32-bit floating point precision. So we have data on the host, data on the device. So this is what this x_h means on the host. So the host prepares the input, allocates also memory for the output, and that gets copied and also initialized on the device. So the x_d is the memory allocation on is the name of the array of the vector on the device. So one needs still to be aware of these memory transforms. But the setup is still very short compared to what you would need to go through in a C program. The launching of threads here, it is a simple, basic getting started example. We launched 32 threads, and we do this on the device data. So the complete code will also compare with the CPU, and there is also the transfer from the device to the host that is defined in the complete code. The point being that doing GPU acceleration looks extremely technical at first, and it is indeed getting used to, but with high-level programming languages like Julia, one gets a handle on this fairly quickly. All right, so the notion of data staging is important. It's of very high priority in the best practices in the GPU acceleration. So I followed the textbook on massively parallel programming, the second textbook that we are using. So I hope that the Julia program helped with the third exercise. The point of the third exercise is to rearrange the computation that it uses coalescing, and see whether you notice a difference. So it's mainly important that you understand the rearranging of the output data, of the way the output is done. I gave not a C program, but I give a very short kernel that is the copy kernel. You can use that copy kernel also in Julia, so that would be another exercise. So see if with Julia you can see the effect of the offsets, of the different offsets, and that would mean that as you load data into shared memory, so if you even copy two arrays, that if the elements in the matrices are far apart, that the copying will take longer because of the effect that adjacent elements in global memory can be accessed more efficiently than elements that are far apart. So then there is this running example of matrix-matrix multiplication that we have been using throughout this GPU acceleration part in the course. So we are getting very close to completely understanding this example. So the middle exercise is also addressing that important parallel programming pattern. Okay, so I hope this was interesting. So we still have one more lecture that addresses the performance considerations. There are still the limitations from available registers that must be taken into consideration when determining the configuration parameters when launching kernels.